Welcome to this deep dive into the scientific principles that Michelin-star chefs use to create extraordinary culinary experiences. Today we're going to explore the physics, chemistry, thermodynamics, and material science that separates exceptional cooking from ordinary cooking. Let's start with one of the most fundamental chemical reactions in cooking, the Maillard reaction. This is the secret behind the rich, complex flavors in seared steaks, toasted bread, and roasted coffee. What exactly is the Maillard reaction? It's a chemical reaction between amino acids and reducing sugars that occurs when food is heated above 140 degrees Celsius. When amino acids and sugars are heated together above 140 degrees Celsius, they undergo a complex series of reactions that create hundreds of different flavor compounds, browning pigments, and aromatic molecules. Michelin chefs understand that temperature control is critical. Too low, and you don't get the reaction. Too high, and you get bitter, burnt flavors instead of the desired complexity. The optimal temperature range is between 140 and 180 degrees Celsius. This is why professional chefs use precise temperature monitoring. Let me give you a concrete example. When searing a steak, chefs heat the pan to exactly 230 degrees Celsius. They sear for precisely 90 seconds per side. This creates maximum Maillard reaction on the surface, while keeping the interior at the desired temperature. Now let's talk about heat transfer. Michelin chefs are masters of thermodynamics, understanding exactly how heat moves through different materials. There are three fundamental modes of heat transfer in cooking: conduction, convection, and radiation. Elite chefs use all three strategically. Conduction occurs when a hot pan touches food directly. Convection happens when hot air or liquid circulates around food. Radiation occurs when infrared waves from a broiler or grill transfer energy to food. Why do top chefs prefer copper pans? The answer lies in thermal conductivity. Copper has a thermal conductivity of 400 watts per meter Kelvin, compared to 80 for stainless steel. The thermal conductivity of copper is 400 watts per meter Kelvin, while stainless steel is only 80 watts per meter Kelvin. This means copper transfers heat 5 times faster. This 5 times faster heat transfer means instant temperature response. When you adjust the flame, the pan temperature changes immediately. You also get perfectly uniform heating with no hot spots. Let's move to emulsification. This is the science behind sauces like hollandaise, mayonnaise, and vinaigrettes. Understanding emulsion chemistry is crucial for Michelin-level sauces. Here's a question. Oil and water don't naturally mix. Why not? The answer is molecular polarity. Water molecules are polar, with positive and negative ends. Oil molecules are nonpolar. An emulsifier is a molecule with both polar and nonpolar ends. One end loves water, the other end loves oil. The emulsifier acts as a bridge, allowing tiny droplets of oil to remain suspended in water. The magic ingredient in traditional emulsions is lecithin from egg yolk. Lecithin has a hydrophilic head that attracts water and a hydrophobic tail that attracts oil. For a stable emulsion, the oil droplets must be smaller than 1 micrometer. This is achieved through vigorous whisking or blending. Temperature control is also critical. For hollandaise, the optimal temperature is between 60 and 65 degrees Celsius. Below 60, the emulsion is too thick. Above 65, the proteins denature and the emulsion breaks. Now let's discuss Sous vide, which is French for under vacuum. This technique perfectly demonstrates thermodynamic precision in cooking. What makes sous vide scientifically superior? The answer is precise temperature control and uniform heat distribution throughout the entire piece of food. Food is sealed in a vacuum bag and immersed in a precisely controlled water bath. The water temperature is held constant to within 0.1 degrees Celsius. For example, to cook a steak to medium rare perfection, set the water bath to exactly 55 degrees Celsius. After 2 hours, the entire steak reaches 55 degrees, edge to edge. This follows the heat transfer equation. Q equals mc delta T, where Q is heat energy, m is mass, C is specific heat capacity, and delta T is temperature change. The beauty of sous vide is that the food can never exceed the water temperature. This eliminates overcooking. The entire piece reaches the target temperature uniformly. Different proteins denature at specific temperatures. Myosin in meat denatures at 50 degrees. Actin denatures at 66 degrees. Collagen converts to gelatin at 70 degrees. Chefs use this knowledge to achieve precise textures. Let's explore spherification, a technique pioneered by Chef Ferran Adrià. This is pure applied chemistry at the molecular level. Spherification uses sodium alginate and calcium chloride to create liquid spheres with a thin gel membrane. The chemistry is fascinating. A liquid containing sodium alginate is dropped into a calcium chloride bath. At the interface, calcium ions cross-link the alginate polymers, instantly forming a gel membrane. The reaction is: two alginate molecules with negative carboxyl groups react with one calcium ion to form a cross-linked gel network. The membrane forms in milliseconds, creating a sphere with liquid interior and thin gel exterior. This allows chefs to create caviar-like spheres of any flavor. The concentration matters tremendously. The optimal alginate concentration is 0.5 to 1%. Too little, and the sphere is too fragile. Too much, and it becomes rubbery. Now let's talk about sugar crystallization. This is material science at the microscopic level, critical for making perfect caramel, fondant, and candy. Sugar can exist in two states: crystalline, where molecules are organized in a regular lattice, or amorphous, where molecules are randomly arranged. In the crystalline state, sugar molecules are arranged in a precise, repeating pattern. In the amorphous state, they are randomly distributed. For smooth caramel or hard candy, we want the amorphous state. For fondant or fudge, we want controlled crystallization with tiny crystals. How do chefs prevent unwanted crystallization? They use interfering agents like corn syrup, cream of tartar, or lemon juice. Acids cause sucrose inversion, breaking it into glucose and fructose. These different sugars interfere with crystal formation, keeping the mixture smooth. Temperature also controls crystal size. For fondant, the syrup is heated to 115 degrees Celsius, then cooled to 40 degrees before agitation. This creates millions of tiny crystals, instead of large, grainy ones. Let's explore pressure cooking, which uses thermodynamic principles to dramatically reduce cooking time while improving texture. Why does pressure cooking work? The answer lies in the relationship between pressure and boiling point. The boiling point of water is a function of pressure. At normal atmospheric pressure, water boils at 100 degrees Celsius. But at 2 atmospheres of pressure, water doesn't boil until 121 degrees Celsius. This allows cooking at much higher temperatures while keeping food moist. Inside a pressure cooker, pressure builds up to about 15 pounds per square inch above atmospheric. This raises the boiling point and accelerates chemical reactions. Collagen breakdown follows the Arrhenius equation. Increasing temperature from 100 to 121 degrees more than doubles the reaction rate. A 4-hour braise becomes a 45-minute pressure cook. Michelin chefs use pressure cookers for stocks and braises. The high pressure extracts more gelatin from bones and breaks down tough connective tissue rapidly while preserving moisture. Now let's discuss gelification using hydrocolloids. These are molecules that bind with water to create gels of various textures. Different hydrocolloids have vastly different properties. Gelatin is thermoreversible, agar is firm and brittle, carrageenan is elastic, and methyl cellulose gels when heated. Gelatin melts at body temperature. Agar creates firm, brittle gels. Carrageenan is elastic. Pectin is used for jams. Methyl cellulose uniquely gels when heated, useful for hot foams. Concentration determines gel strength. For gelatin, 0.5% creates a soft gel, 2% creates a firm gel, and 4% creates a rubbery gel. Gel strength is proportional to hydrocolloid concentration, but the relationship is nonlinear. The pH and presence of ions dramatically affect gelation. Agar gels are pH stable, but carrageenan requires potassium ions. Pectin needs low pH and sugar to gel properly. Example: to create a caviar-like sphere with agar, the mixture is heated to 90 degrees to dissolve the agar, then dripped into cold oil using a syringe. The agar instantly gels in spheres. Let's explore fermentation and enzymatic reactions. Top chefs use controlled fermentation to develop complex flavors through biochemistry. Fermentation is essentially controlled microbial metabolism. Microorganisms consume sugars and produce acids, alcohols, and aromatic compounds. Microorganisms break down glucose into various products. Lactic acid bacteria produce acid. Yeast produces alcohol and carbon dioxide. Both produce hundreds of aromatic compounds. Temperature precisely controls which organisms dominate. At 18 to 22 degrees Celsius, yeast dominates for bread. At 30 to 35 degrees, Lactobacillus dominates for yogurt. Salt concentration also selects organisms. At 2 to 3% salt, beneficial bacteria thrive while pathogens are inhibited. This is critical for safe fermentation. Fermentation time is a function of temperature, salt concentration, and pH. Chefs control all three variables precisely. Example: dry-aged beef uses controlled enzymatic breakdown. Calpain and cathepsin enzymes break down muscle proteins over 28 to 45 days at 1 to 3 degrees Celsius, creating tender meat with concentrated flavor. Finally, let's discuss nucleation, which is critical for controlling texture in everything from ice cream to chocolate. Nucleation is the initial formation of a new phase from a metastable state. It determines crystal size and number, which directly affects texture. In ice cream, the goal is millions of tiny ice crystals. Large crystals feel grainy and icy. Small crystals create smooth, creamy texture. Many small ice crystals create smooth texture. Few large crystals create grainy, icy texture. The difference is nucleation control. Rapid cooling promotes many nucleation sites. This is why ice cream machines churn while freezing. Agitation and fast cooling create millions of small crystals. Stabilizers like guar gum prevent crystal growth during storage. They increase viscosity, which slows molecular diffusion and inhibits crystal enlargement. Chocolate tempering is another example. Cocoa butter can crystallize in 6 different forms. Only form 5 creates the desired snap, gloss, and melt. The tempering process: heat to 45 degrees to melt all crystals. Cool to 27 degrees to form stable form 5 nuclei. Then warm to 31 degrees to melt unstable crystals while keeping form 5. This 3-temperature process seeds proper crystallization throughout the chocolate. The result is perfect snap, shine, and texture. Without proper tempering, chocolate blooms, developing a white coating and poor texture. With perfect tempering, it has mirror shine and crisp snap. Now let's talk about how Michelin chefs integrate all these principles into a single dish. Consider a sous vide duck breast with cherry gastrique. This single dish uses at least 6 of the principles we discussed. First, the duck breast is sous vide at 58 degrees Celsius for 90 minutes. This uses precise temperature control and thermodynamics for edge-to-edge perfection. Second, the breast is quickly seared in a screaming hot pan. This creates Maillard reaction browning and flavor development in just 45 seconds per side. Third, the cherry gastrique uses controlled sugar caramelization up to 175 degrees. Then, acid addition prevents crystallization. The sauce is finished with cold butter, creating an emulsion. Fourth, plating on a warmed plate uses thermal conductivity to keep the dish at optimal serving temperature throughout the dining experience. Every element of this dish demonstrates deep scientific understanding. Temperature precision, chemical reactions, phase transitions, and material properties are all carefully controlled. Let me summarize the key scientific principles that separate Michelin cooking from ordinary cooking. First, the Maillard reaction creates flavor complexity, but only in the precise temperature range of 140 to 180 degrees Celsius. Second, understanding thermal conductivity and heat transfer allows perfect control of cooking processes. Third, emulsification chemistry creates stable, luxurious sauces through molecular bridges between oil and water. Fourth, sous vide applies thermodynamic principles for unprecedented precision and consistency. Fifth, techniques like spherification apply chemistry directly to create novel textures and presentations. Sixth, controlling crystallization in sugars, ice cream, and chocolate determines final texture. Seventh, pressure cooking exploits the pressure dependence of boiling point to accelerate reactions. Eighth, different hydrocolloids create precisely controlled gel textures for specific applications. Ninth, fermentation is controlled biochemistry that develops complex flavors through microbial metabolism. 10th, Controlling nucleation determines crystal size and thus the texture of frozen and crystalline foods. The fundamental difference between Michelin-star cooking and ordinary cooking is the scientific rigor applied to every single decision. Temperature, time, concentration, pH, and material properties are all precisely controlled. Cooking at the highest level is not art versus science. It is art informed by rigorous science. Every technique, every ingredient choice, every temperature reflects deep understanding of physics, chemistry, and materials science. Thank you for joining me on this scientific exploration of what makes Michelin-star cooking extraordinary. Remember, excellence in cooking comes from understanding and controlling the fundamental scientific principles that govern flavor, texture, and transformation.